Hey everyone, welcome to section 4.8, Antiderivatives. As you might be able to guess from the title, this section is all about undoing derivatives. I know, you were just getting used to taking derivatives and now we're going to ask you to do it the other way around. So up to now, our problems have looked something like this. If f of x is equal to x cubed plus cosine of x, find f prime. Take a second to make sure you know how to do this problem. Did you get that f prime was equal to 3x squared minus sine of x? But see, starting in this section, the question's going to go the other way around. Let me word it this way. I'm thinking of a function, g of x, where g prime of x is equal to 3x squared minus sine of x. Find g. This problem is a very natural question to ask. If you think back to where this class started, the idea was that we wanted to find the instantaneous velocity given the position. This question just reverses that. It asks you if you know the instantaneous velocity, can you figure out your position at any given time? So before we move on, why don't you try to answer my question? What function g am I thinking about? You should pause the video here and give yourself time to think about it. Did you get that g should be x cubed plus cosine of x? Well, even though the derivative of that function is 3x squared minus sine of x, it wasn't the function I was thinking about. I was instead thinking about the function x cubed plus cosine of x plus 101 over 103. Before we move on, let me introduce the term antiderivative. Both these expressions are antiderivatives of 3x squared minus sine of x, because the derivative of both of them is 3x squared minus sine of x. Notice that I said an antiderivative. Any given function can have many antiderivatives, as we will see shortly. So why were you unable to guess the function I was thinking about? To explain this, let's look at these two theorems that we've seen before. Way back in chapter 3, we saw that any constant function has derivative 0. In 4.2, we saw that the opposite is also true. If your function has derivative 0, it had to have been a constant. Putting this all together, we see that the only functions whose derivatives are 0 are constants. So this means there were a lot of possible answers to my original problem. In fact, had I replaced 101 over 103 by some horrible real number that cannot be expressed by a finite number of symbols, you could have spent your entire mortal life using all of the computing power of Earth and never have found the g I was thinking about. Notice that all these guesses are antiderivatives of 3x squared minus sine of x. But what do they have in common? They all look like some constant added to x cubed plus cosine of x. Since we aren't using complex numbers in this class, we'll just ignore guess 14 altogether. This observation allows us to come up with a lot more antiderivatives. In fact, we can come up with one for every real number, which means there's an infinite number of possible answers to this original problem. This kind of problem is often referred to as being ill-posed, since it doesn't have just one answer. There are a variety of ways we could rephrase this question, but for the time being, let's ask for all of the antiderivatives instead of just one of them. Our answer to this question must be the original function we started with, x cubed plus cosine of x, plus some arbitrary constant which we denote here with this capital letter C. Notice that there are an infinite number of antiderivatives. For those of you who've maybe taken a calculus class before and got annoyed when you only got partial credit for forgetting that C, you should consider yourself lucky because you forgot an infinite number of the answers. Remember, the question is what are all the antiderivatives, not what is one antiderivative. Now that we're taking antiderivatives, we are thinking of the function we start with as the velocity at any given time. So from this point of view, the antiderivative tells you the position at any given time. But if you think about it, if you do not know where you start, the velocity doesn't help you know where you are. Driving 10 miles per hour north and then 5 miles per hour west gets you to different places depending on whether you start in San Diego, Las Vegas, San Francisco, or Cal Poly Pomona. And that's what this plus c captures. It tells you this is how far you've gone, and plus c represents where you started. So hopefully you're asking yourself, how do I know that those are all the antiderivatives? I'm sure that those earlier theorems that only constants have zero derivatives gave you a good idea of why that is. But here's a theorem that formalizes everything we've just been saying. It says that once you have an antiderivative capital F of a function little f, then any other antiderivative capital G of x is just a constant plus capital F. The notation of using capital letters to refer to antiderivatives of functions will appear throughout the remaining videos and in Calculus 2 and sometimes Calculus 3. So this theorem tells us that our answer from before was in fact correct. So I'm going to go through the proof of this theorem because the method we use is going to show up in your linear algebra and differential equations class in other forms. Also, for those of you who are math majors and will eventually take upper division math classes, this trick will show up in a lot of other classes. So here's the idea. Let's take a function little f and two antiderivatives, capital F and capital G. So we want to show that g is just a constant plus the function f. The trick is going to be this. Instead of trying to deal with f and g separately, we're going to look at the difference, g minus f, and show that that's a constant. We're going to do this by showing that the derivative of g minus f is equal to 0, and then using our theorem from before. This is the big trick I referenced before. If we have information about two things, instead of studying each thing individually and trying to make them look like one another, we study their difference. So let's do it. We take the derivative of capital G minus capital F of x, and because they both have the same derivative, little f, it cancels and goes to 0. So g minus f must be a constant. Solving for capital G of x, we get that capital G of x is equal to capital F of x plus a constant. So now that we know our original answer to this question was correct, we'll deal with the second problem. We don't want to have to say, find all functions g such that g prime of x equals 3x squared minus sine of x every single time we want to talk about an antiderivative. So what we're going to do is we're going to introduce notation that is equivalent to it. So from now on, instead of writing that question, we're going to use this collection of symbols you see below. I think it's important to see the symbols in this context before learning all their names, because at the end of the day, this collection of symbols represents a phrase in English. So when we write find or evaluate this collection of symbols, we are saying find all of the antiderivatives of 3x squared minus sine of x. We would write our answer to this problem as you can see below. And again, it's very important to remember that because we want all of them, we need that plus c. So let's introduce everybody formally now. The fancy s-looking symbol is known as the integral sign. The function f inside it is known as the integrand of the integral. And that dx tells you the variable of integration is x. That dx needs to be there for technical reasons. And I know right now it'll seem a little bit superfluous because we're only dealing with one variable. But when you get to Calc 3, it's going to be very important to know what variable you're integrating in. So keeping that dx is going to be very important. So get in the habit now of always writing it down. So when put all together, these symbols are read as the indefinite integral of f with respect to x. And it represents the collection of every antiderivative of f. I understand that these new symbols as a whole may be overwhelming, but there's a very good reason why we want to use this collection of symbols, and it'll become evident in Chapter 5. I think it's important not to forget that these symbols just represent the set of antiderivatives. So if you remember that, these symbols are just not as intimidating. One last thing, sometimes this is read as the indefinite integral of f of x dx, instead of saying with respect to x. I'll be using all three of these phrases throughout this video to try to get you comfortable with the fact that they're all the same. Great, so now with our new notation in hand, and the fact that all antiderivatives are just a constant plus any given one antiderivative, we can now answer a variety of questions like this. For example, we know that the derivative of x is 1. So the indefinite integral of 1 with respect to x is just equal to x plus a constant. Similarly, since the derivative of x squared is 2x, we know that the integral of 2x dx is just x squared plus a constant. The derivative of sine of x is cosine of x, so the collection of antiderivatives of cosine of x is just sine of x plus a constant. If you know the derivative of something, you know its antiderivative. E to the x is its own derivative, so the integral of e to the x dx is just e to the x plus a constant. As you may be noticing, most of the questions involved with this section are rather short, so there will be a lot of examples, and I will do my best to pause before talking about the solutions. So it'll be on you from now on to pause the video as much as you need to try the problems on your own. So let's look at a few more antiderivatives. First of all, we know that the derivative of arctangent is 1 over x squared plus 1, so not surprisingly, the indefinite integral of 1 over x squared plus 1 with respect to x is just arctan plus c. I'm using this example to point out a notation that is common. When we are integrating a quotient with a 1 in the numerator, we often write the dx as the numerator, but it means the same thing. We know that the derivative of cosine of x is minus sine of x, which means that the antiderivative of sine of x is actually minus cosine of x plus any constant c. I specifically point this particular example out because it is common for people to forget the minus sign. Since the derivative of cosine of x is negative sine of x, so the antiderivative of sine is negative cosine plus c. Finally, let's look at one more example where mistakes are often made. The integral of 1 over x dx is actually the logarithm of the absolute value of x plus c. The absolute value of x isn't just there to torture forgetful calculus students, though. You have to remember when we're talking about antiderivatives, we care about antiderivatives on the domain of the function we are studying. The domain of 1 over x is all real numbers but 0, but the domain of logarithm is only the positive reals. Using the chain rule, if we were to compute the derivative of the logarithm of minus x for negative values of x, we would get 1 over x as well. Thus, the natural logarithm of the absolute value of x takes care of both the cases when x is positive and when x is negative. So let's turn our attention to another example. In this one, let's compute the definite integral of x with respect to x. We saw on 2 slides ago that the definite integral of 2x with respect to x has to be x squared plus a constant. So the question is, what do we do without having the 2? If you already see what to do, or you've seen this before, that's fine. What's important here is the concept underlying this, not this specific example. What we really need to do is figure out how constants interact with integration. To figure this out, we will ask, how do derivatives interact with constants? This brings us back to the constant multiple rule for derivatives that we saw back in section 3.3. It says that if you take the derivative of a function times a constant, it is just that same constant times the derivative of the function. So that means antiderivatives have to have this same property. With this in mind, let's compute the antiderivative of x. We know that the antiderivative of 2x is x squared plus a constant. We also know we can pull the 2 out of the integral on the left, and thus twice the integral of x has to be equal to x squared plus a constant. So we solve for the integral of x with respect to x, and find that it's equal to x squared over 2 plus the constant over 2. But remember, the c we add is just a generic constant, so we may rewrite it just as a c, because dividing it by 2 does not change the fact that it's a constant. If that makes you uncomfortable, you can also keep c over 2. It's the same. Now see if you can find the integral of x squared dx. Pause the video here if you want some time to try it for yourself. Using the same trick as before, we know that x cubed has derivative 3x squared, so we can solve for the integral of x squared dx and find that it's equal to 1/3 x cubed plus c. Now why don't you try the next example? Find all the antiderivatives of the square root of x. While at first it might look trickier than the example we just did, remember that the square root of x is equal to x to the 1/2. So again, we know that x to the 3/2 has derivative 3/2 times x to the 1/2. Then it's just doing the same thing we did before. We find that the integral of the square root of x dx is equal to 2/3 x to the 3/2 plus a constant. So in reality, what are we doing? We are reverse engineering the power rule from derivatives. The power rule from derivatives told us that the derivative of x to the n was just n x to the n minus 1. So we know in order to take the antiderivative of x to the n, the power must increase by 1. But we also know if we took a derivative of x to the n plus 1, we'd get an extra factor of n plus 1 out front. So we divide by n plus 1 in order to cancel out that factor. This procedure is summarized at the bottom of this slide with the quote-unquote power rule for antiderivatives. Don't forget to add c. The most important part of this is you should remember that you can't do this when n is equal to negative 1. One way to see it is that our formula would have denominator 0 if n was equal to negative 1. Another way to see it is if you have x to the negative 1, you really have 1 over x, whose antiderivative we already know is the logarithm of the absolute value of x plus c. So what other derivative rules have an antiderivative analog? Well, one of them is what we call the sum or difference property, which says that the derivative of the sum or difference of two functions is just the sum or difference of their derivatives. Similarly, the antiderivative of the sum or difference of two functions is the sum or difference of their antiderivatives. With this new property in mind, why don't you try this example? So remember, we're going to go through this a little quickly, so feel free to pause as much as you need to make sure you understand every step. So at first this seems like a bit much. But just remember, we know how to do the antiderivatives of each individual term on their own. Then it's just about putting it all together using the constant multiple property and the sum and difference properties. And we get our final answer. If we included plus c for each of the antiderivatives listed above, we would end up getting plus 8c at the end. But just like before, 8 times c is still a constant, so we can just write c. So are there any more properties of derivatives we can exploit to find antiderivatives? The answer is yes, and we'll see later in chapter 5 a method called u-substitution, which can be used to undo a chain rule. The method of integration by parts, which you'll see in Calc 2, uses the product rule for derivatives in a way to be able to compute some other antiderivatives. So let's look at this example, which is very much related to the chain rule. Take a moment and see if you can find all the antiderivatives of sine of 2x. So go ahead, pause the video, and give it a go. So we guess the antiderivative has something to do with cosine of 2x, since the derivative of cosine of 2x is minus 2 sine of 2x. So at this point we can do what we did before and realize that minus 1/2 cosine of 2x must have derivative sine of 2x, which means the antiderivative of sine of 2x is negative 1/2 cosine 2x plus c. Now why don't you try the second example? Find the indefinite integral of e to the minus 3x with respect to x. So using that the derivative of e to the minus 3x is equal to minus 3 e to the minus 3x, we can work backwards and see that the integral of e to the minus 3x dx must be equal to minus 1/3 e to the minus 3x plus a constant. Both these examples had a function whose antiderivative we knew, but we plugged in some constant times x. So in order to find their antiderivatives, we were in some sense undoing a chain rule. In the first one we had sine of 2x. In the second one we had e to the minus 3x. Notice that the antiderivatives were almost the same as if we had just plugged in x instead, except for two major differences. The first major difference was that the inside function of the antiderivative was still that constant times x. The second one was that we had to divide by that constant in order to cancel out the eventual chain rule. This statement here captures what we just said. If we already know that big F is an antiderivative of little f, then for any non-zero constant k, the indefinite integral of f of kx dx is just 1 over k, capital F of kx plus c. So let's try two more examples before we call it a day. So first, pause the video and try to evaluate this integral. So if you thought there might be some fancy trick for dealing with this, there isn't. You have to remember that 1 over the square root of 1 minus x squared is the derivative of arc sine of x. If you instead got that this is the derivative of the negative arc cosine of x, you're not wrong. So your answer to this could have been either arc sine of x plus a constant or minus arc cosine of x plus a constant. If you're asking yourself, how can both arc sine and negative arc cosine be antiderivatives for the same function? Also notice that since arcsine and negative arc cosine are antiderivatives for the same function, they must differ by a constant. In fact, in this graph, you can see that minus arc cosine is just arcsine shifted down by pi halves. I will say this one more time now. You need to know the antiderivatives when the inverse trig functions are involved. About a third of Calculus 2 focuses on integration techniques, which are methods you can use to compute more complicated antiderivatives. One of those techniques is called trig substitution. The trick in that technique is to make whatever integral you're trying to do look kind of like a trig or inverse trig integral. So at some point, this type of integral needs to become a reflex. Now let's try one last example. It is related to the one we just did, and the theorem that came before it. So pause the video and take a minute to try it on your own. The key to this example is to realize the integrand looks like the integrand in the previous example, but with 3x plugged in for x. That means the antiderivative must be that same arcsine, but with a 3x plugged into it, all times 1/3, plus c. If you put minus 1/3 arc cosine of 3x plus c, you are also right. So honestly, I could go on for a while with more of these dry examples, but neither you nor I want to do that, so instead let me just finish by showing you this table from our book. This table shows you the antiderivatives of a variety of different functions. For example, if you wanted to find the antiderivative of secant squared of 4x, you could use line 4 to find that it's 1/4 tangent of 4x plus c. Just to hammer home how important antiderivatives are, here's a picture of an old book that belonged to my friend's grandfather, who was an aerospace engineer his whole career. The entire book is just filled with integrals that commonly come up in a variety of science and engineering problems. Granted, now we have computers, so it's not necessary to have these books handy. Interestingly enough, you can actually do integral 108 when a is equal to 0 after just watching this video. By the end of the class, you'll be able to do it even when a is not 0. This ends chapter 4, but in many ways this should have been the first section in chapter 5. Everything we discussed here will be the backbone of everything we do for the rest of the class, and what you do for a big chunk of Calculus 2 and eventually 3. So it's very important that you get comfortable with both the idea of an antiderivative and the computational aspects of finding these antiderivatives. I'll see everyone in chapter 5.